Hello everyone. This is GP2 SciTube Academy. SciTube Academy. So the modern physics, applied modern physics course, special theory of relativity as unit 1. So I just want to present or give a lecture on this topic. So the outline is here. Special theory of relativity. Under the special theory of relativity, we will see inertial reference frame and Galilean transformation, postulate of special theory of relativity, Lorentz transformation, and length contraction, time dilation, and also the dynamics of special theory of relativity. Of course, we will not cover all the topics in one video. Just we will try to see the first few subtopics in this video. So let's start. To start with, we will try to define what's meant by Lorentz, the inertial reference frame in a Galilean transformation. Normally, what is inertial reference frame? So to describe a certain motion, we place a coordinate system at some point, either on the object or outside the object, on the object or on the body or outside the body. And this is what we call a coordinate system or a reference frame. So we have two kind of reference frame. One is inertial reference frame and the other is non-inertial reference frame. Inertial reference frame is a frame either it is at rest or moving with constant velocity. So that means that the inertial reference frame is a frame of a certain object or a certain observation, and that the frame is at rest with velocity 0 or the frame is moving with constant velocity. In that case, the force is the net force is 0 or acceleration is 0 of the system or the frame. This is what we call inertial reference frame, and non-inertial reference frame is the reference frame which is accelerating. So in here we will try to see this frame. In a Galilean transformation, we will apply this frame. So we are considering two frames. One is stationary, the other one is moving with constant velocity. Of course, then this kind of reference frame is it is an absolute. It doesn't. It's an absolute inertial reference frame. That means that any system moving with constant velocity with respect to an inertial reference frame must also be in an inertial reference frame. This means that if you perform two experiments, one is in a moving frame and another one is in a stationary frame, the experimental result will give you the same output or the same result, or the experiment will give you the same result, or the laws of mechanics will be the same either the frame is stationary or moving with constant velocity. For example, let's consider the case here. So here, as you can observe, in the first vehicle or in figure A, a person is throwing a certain object upward, and if he observe the situation, so the object motion is upward and downward. If somebody observe outside from the car this situation, it will look the same thing. It will he can observe, or the person can observe the same situation. But what will happen if the person outside the car, but the car is moving with constant velocity and the person inside the car is throwing an object upward? So the person outside the car observes a kind of parabolic motion or parabolic kind of observation, but the person in the car will observe the object's motion upward and downward. So whatever the observation is, whatever the situation is, the Newton laws of motion or conservation of energy or conservation of momentum over any other physical laws will give you the same result if you try to treat them. So suppose that some physical phenomena which we call an event occurs and is observed by an observer at rest in inertial reference frame, and this event's location and the time occurrence can be specified by 4-coordinate system. You can express the situation or the event's condition with respect to position and time in 4-coordinate. That means x, y, z, and time is there. So you can express the event in terms of this. So what we want to see here is Galilean transformation, a transformation of the inertial reference frame. One is moving with constant velocity, another is stationary. So we want to observe the situations, the event in terms of these two reference frame. So let's consider, for example, consider two inertial reference frame, S and S prime. S is the one that you see here, and S prime is here, but S prime or reference frame S prime is moving with constant velocity v, and with respect to the stationary reference frame, which is S. So in this case, at the time t0, both are in the origin, and then after a certain time the moving frame will move with a velocity v, and when you multiply the time t, you get a distance from the stationary reference frame to the moving reference frame. And if you try to express the event p in terms of S frame and S prime frame, in terms of S prime frame, it is at a position of x prime, but in the y direction and the z direction, the event, the reference frame is not moving. The reference frame is moving only in x direction. Therefore, the other parameter, the z and the y part of the components of the event observation with respect to S prime is the same. So it's not changing with x and y and z. So you can express x distance from the stationary frame to the event in terms of vt plus x prime. So vt plus x prime is x, and y is equal to y prime, and z prime, and t prime. So this is a Galilean transformation. You can express the moving reference frame observation of an event with respect to express the event's observation with respect to stationary frame. So this is the situation. But if you reverse the case, that means if you want to see the inverse transformation, you can apply this. That means x prime, the moving reference frame position of an event with respect to the stationary one can be x minus vt, minus vt, and y is y prime and y is the same, z prime and z prime, z is the same, and t prime is the same. So in the Galilean transformation, the coordinates or the position of transformation looks like this. The inverse is this one, and the direct expression is this one. So you can apply this technique to transform from a moving frame to stationary one, or from the stationary to a moving frame, by observing a certain event in order to express a certain event in terms of these two inertial reference frame. So Galilean transformation of speed, or the velocity transformation of can also be obtained from the position transformation. That means we know that x prime is x minus vt. Then if you derive it with respect to, that means dx by dt, dx prime by dt prime, and you get dx prime by dt prime or dt, because t and t prime are the same, so t is equal to dx by dt minus v. So dx by dt is vx or ux, the velocity of the nav, and with respect to the stationary one, and vx prime is the velocity of the event with respect to the moving reference frame. So you can express, so vx prime is equal to vx minus v, and in the y direction, the z direction, the position is not changing in time. So even the frame of reference is moving in one direction only, so we can get vy prime is equal to vy, vz prime is equal to vz, and t prime is equal to t. And so the Galilean transformation of velocity can be summarized as follow. So vx or ux is just v, and u is the same, so we are talking about the velocity. So ux is equal to ux prime plus v, and ux prime is equal to ux minus v, and this is one is the reverse of the error, the inverse of the error, and then this you can see the expression. So let us see examples. So the first example here is here. Let me move to this one. That means a passenger in a train moving at 30 meter per second passes a man standing on a stationary platform at a time t is equal to t prime is equal to 0. Then 20 seconds later, the train passes him. The man on the platform determines that a bird flying along the track in the same direction, that means in the x direction, as the train is 800 meters away. What are the coordinates of the bird as determined by the passenger with respect to the moving reference frame? How is the bird's position and the time expression or coordinate system, the four coordinate systems? Therefore, it's given that as a solution, it's given that x, y, z, and t is given. The bird's location with respect to stationary platform. So 800 meters, 0, y, 0, z, and 20 seconds. This is x, y, and x, y, z, and time. And we want to find out x prime, y prime, z prime, and t. So x prime is obtained by subtracting x minus vt, or by computing this x minus vt. So 800 minus 30 times 20 to 600, when you subtract, you will get 200 meter. This is, so therefore the coordinates, the bird's coordinates as determined by the passenger are this x prime, y prime, and d prime, and t prime is the 200, 0, 0, and 20 seconds. This is, I think this is a good example to see the effect of this transformation. And another example is here. I will discuss it later another time. For today, I think this is all about. First, we define what's inertial reference frame, and then we try to see Galilean